Moving sounds. This is lesson 2 in the sounds topic 7L. Objectives for this session. First, to describe how sound moves through materials, and secondly, to explain why sounds get fainter the further you get away from their source. Sounds are created by particles vibrating. That means that sounds require a medium. A medium is anything that is made of solid, liquid or gas, anything made of particles. That also means that sounds cannot pass through a vacuum such as space, because in a vacuum there are no particles, so there is nothing to carry the sound. In the picture there, the astronauts working outside the International Space Station couldn't hear each other, but they can communicate by means of radio, and that's because radio waves can pass through a vacuum. Similarly, if there was an explosion in space, the astronauts wouldn't hear it because there is nothing to carry that sound to them through the empty vacuum of space. We're going to look at how a sound wave is formed. And you see here, a vibrating loudspeaker makes the air particles next to the speaker move forwards and backwards. So the air particles are vibrating. Those air particles then contact other air particles and make them vibrate, and the vibrations spread out through the air. A sound wave is formed. This means that in some places the air particles are squashed together, which gives them a high pressure, and in other places the particles are spread out and they have low pressure. So sound is a pressure wave because there are repeating patterns of high and low pressure. If you look at the diagram, the animation, the places where the particles are densely packed together are high pressure, and that's shown on the graph underneath, and the bits where they're spread out are low pressure. If you look at the red particles, you'll see that they're not actually moving along the wave. This is another still picture showing a representation of a sound wave. As the loudspeaker is turned on, initially all the air particles are evenly spread, but when the loudspeaker starts to vibrate, that pushes some of the air particles together, forming bands of high pressure, and in between those bands of high pressure, the air particles are further apart, and they're at a lower pressure. The air particles are moving forwards and backwards. They are not being transferred along the wave. Only energy is moved along the wave. The amplitude is the maximum movement of an air particle from its starting position. And you can see that by the blue arrow. That is the amplitude of one wave or air particle. And the red arrow shows the total movement of that particle, and you'll see the total movement is twice the amplitude, because the amplitude is from the middle, which is the starting position. And if you look at the lower part of the picture, you'll see the particles move a very small amount, but the energy transfer is all the way along the wave. It's very important you don't make the mistake of thinking that the particles move along the wave. Only energy is being transferred. So, as I said, the amplitude of the wave is the distance moved by the particle from its starting position. And the bigger that amplitude is, the louder the sound will be, and the more energy is being transferred along the wave. So now let's look at the second objective to explain why sounds get fainter as you get further from the source. Sounds spread out from their source, And a bit like ripples in a pond, but sounds do it in all 3 dimensions rather than 2 dimensions on a pond. And that means the further away you are from the source, the more that energy has spread out and the thinner it's become. So there's less energy and the sound will be quieter. Sound travels at different speeds through different materials. And if you look at the table, you'll see, you might think that sound would be quickest through air, but in fact it's not. It's slower through air because the particles are further apart. So the particles are closest together in solids, and therefore sound can move more quickly through denser materials. So sounds travel fastest through solids, then liquids, and they're slowest in gases. Thunder and lightning happen at exactly the same time. The light travels at 300 million meters per second, and that's the fastest speed that anything can travel. So the light reaches your eye almost instantly. The sound wave, however, travels much more slowly, around about 330 meters per second. So every 3 seconds between seeing the lightning and hearing the thunder is about 1 kilometer that sound has traveled. So you can work out how far away the lightning is between the gap between the lightning and the thunder. Every 3 seconds equates to about 1 kilometer away. We're now going to watch a short film, 3.5 minutes, about thunderstorms.
Off on the horizon, they rumble. Rolling across the land, they darken the skies to then spark fire in the darkness, letting out an unmistakable roar. Thunderstorms are rain showers accompanied by lightning and thunder. While violent, these weather phenomena are common, with about 2,000 occurring at any moment worldwide. There are 4 major types of thunderstorms: single cell, which are small, weak, and isolated storms; multi-cell, a common type of storm that includes a cluster of thunderstorms; squall line, a collection of storms that can form a line hundreds of miles long; and supercells, the most intense kind of storm capable of producing tornadoes. All thunderstorms form when warm air in the lowest layers of the atmosphere rises. Called an updraft, this air causes water from the Earth's surface to evaporate and carries the moisture upward to form clouds. The clouds then build and grow, sometimes as tall as 10 miles high. The clouds darken as they fill and become heavy with water. Cool, dry air from the upper layers of the atmosphere, known as a downdraft, then pull this moisture downward, causing it to fall as life-sustaining rain. In addition to helping sustain life, thunderstorms also help maintain the planet's balance of energy and electricity. When energy, specifically in the form of heat, causes water to evaporate, the heat is carried upward with the water vapor. As the vapor condenses and forms water droplets, it releases the heat into the higher altitudes of the atmosphere and cools the Earth's surface. Thunderstorms also help regulate the electrical balance between the atmosphere and the planet. As clouds in a thunderstorm develop, excess positive and negative charges form within them. At a certain point, this buildup of opposite charges leads to the transfer of electrons in the form of lightning. This transference of electricity occurs so quickly that it breaks the sound barrier, a phenomenon that produces thunder. While thunderstorms are necessary for maintaining balance in the atmosphere, they can also be hazardous. Lightning strikes create fires. Excessive rainfall can cause flash flooding, and high-speed winds from tornadoes can destroy homes. Meteorologists study weather systems to try to predict the occurrence of thunderstorms and help ensure the safety of countless communities.
That's it for this lesson. There's two things I want you to do. Make sure you complete the worksheet, which was set as an attachment to this assignment, and also recap the quiz as a multiple choice quiz, which is set as a separate assignment. There's only a few questions in that. It won't take you very long, but it's important you do that because it helps you to consolidate what you've learned so you remember it better for the test.